here we have to find the acceleration of this purely rolling body, which could be any form. It could be a cylinder, it could be a sphere, it could be a disc, it could be a ring. It has a mass m, radius r, and radius of gyration as k. It has been released over here, and without slipping it is coming over here, so obviously there is a friction between this and this, so that it is not slipping over the surface. We are asked to find its acceleration down the plane using energy method. So over here we say, let's say when this goes from here to here, so there is a loss of what? There is a loss of potential energy. And what is the gain? When it goes from here to here, what is the gain? We have gain in translational kinetic energy plus rotational kinetic energy. That is the thing. It will have some translational kinetic energy also, and because of friction, but there is no slippage. As a result, the work done by friction will be equal to 0. Friction is only helping it to change its translational kinetic energy into rotational kinetic energy. So when it comes over here, it has a translational kinetic energy that is half mv square. Apart from this, it is going to have a rotational kinetic energy about this axis O, that is half I omega square. So if you put it over here, this goes through x. So if this is x, the height loss is, this is theta, this is x, so this is x cos theta, so this is x sin theta. So potential energy lost is mgh. Mg, h is what? X sin theta. So this is the loss of potential energy. What is gain of kinetic energy? Gain of kinetic energy, that is gain of translation kinetic energy, is half mv square plus rotation kinetic energy, that is we know about this axis only. We are considering this loss of potential energy as the gain of translational kinetic energy of center of mass plus rotational kinetic energy about this axis only, about center of mass only. So it is going to be half I. I about this is, we can write it as mk square into omega square. Also we know, because there is no slippage, we can use the relationship V is equal to R omega, we can use it. So let's put it over here. So this comes out to be mg x sin theta is equal to half mv square plus half mk square. V is equal to R omega, so omega is equal to V by R. So V square upon R square. We can write it like this. So m, and m, it goes off. So it comes out to be, so gx sin theta is equal to half V square, we can take it as common, half V square, 1 plus k square upon R square. We can write it like this. Now if we differentiate both sides with respect to time, so it comes out to be g is constant, sin theta is constant, because theta is constant. So it comes out to be g sin theta into dx by dt is equal to half 2v dv by dt. This once again 1 plus k square upon r square is constant. So 1 plus k square upon r square. Now what is this dx by dt? Dx by dt is how this x is changing with time. That is the velocity of this only. So this can be written as g sin theta dx by dt is v. So this is 1 by 2 and 2 get cancelled. So v dv by dt is what? It is acceleration only. 1 plus k square upon r square. V and v get cancelled. So a is equal to g sin theta 1 plus k square upon r square. Earlier also we had found this result using the torque equations and the dynamic method, where we had talked about forces, we had talked about torques, and from there we had found the same answer, that is acceleration is equal to g sin theta over 1 plus k square upon r square. Then depending upon, that is, what is the k of this body, from there we have found, that is, which of the bodies will come earliest at the bottom, be it cylinder, be it sphere, be it disc, or be it ring. We had found their k and we have put the value of k over here. If the k is more, the acceleration will be less and this body will take more time. So this way you can use the energy method to even find the acceleration of a body.